One of the many things we may be asked to do is interpolation, and we will show an example of numerical interpolation here. So assume this set of data is given to us. We have the independent variable x and the dependent variable y, which we may also refer to as f of x. So we have x and y or f of x here, right? So this is the kind of an idea. So the table that is shown in front of you is given, right? At different x values, you have different y values. That means, for example, for x is equal to 0.12, the y value is given to be 1.309729. Let us pretend that the value of the function f of x at x is equal to 0.32 is not provided to us. So the data is given for x is equal to 0, 0.12, 0.22, 0.36, 0.40, 0.44, and so on, as you see in this particular column. And we are asked to find out the value of f of x at x is equal to 0.32. So we have to interpolate, right? So if you look at Wikipedia, they say interpolation is a type of estimation. The data point is not available, but we are asked to estimate the value of the function at a certain point so that it is consistent with the rest of the data points to the extent possible. Now, what we can do is, of course, take this x and f of x data and fit a function, an overall function to that data, right? So I can fit a polynomial of some kind to the data because I'm given certain values of f of x at x is equal to 0, 0.12, 0.22, and so on, right? At different values like that. So using the data given here, I can fit a polynomial, if you like, and that would be a global approximation with a function of the given data points. That means the function will kind of try to fit all the data points that are available in the table. And then once I construct that function, then I can put the value of x to be 0.32 and recover the value of f of x or estimate the value of f of x. So that is one way you can do. So we can take x and f of x data, do something called a polyfit, and then you can get the solution, right? You can find out the value of f of x at x is equal to 0.32. So I described something which is called a global approximation using a function for the given data points. But somebody can say, well, if this is the value of f of x at x is equal to 0.22, this is just a cartoon. So at x is equal to 0.22, this is the value of f of x. And at x is equal to 0.36, let's say, this is the value of f of x. So I'm not going to involve the other data points. I'm just going to assume that between x is equal to 0.22 and x is equal to 0.36, I'm going to assume that the function is a linear function. So it shows linear behavior between these data points. So I'm not bothered about the other data points that are given in the table. The query point is here, 0.32. That's the value that is the query point. This is 0.32. I do not know the value of f of x at that point. So what I'm trying to say here is I'm just going to take the two data points, one to the right of the query point and one to the left of the query point from the table. And then I'm going to assume a linear relationship for the function between those two data points. And then I can estimate the value of the function at x is equal to 0.32. Basically fit a line. And once I get the equation of the line connecting these 2 points, then I can put x is equal to 0.32 in the equation of that line and get the value of f of x. So this is what is called a local interpolant. That means I'm doing the interpolation using data points that are very near the query point. And in this particular case, I'm doing local linear interpolation. So what I'm trying to say here with whatever I've said so far is that the interpolant can be a global one using all the data points and the construction of a function, or it can involve only local points. So that is one thing. The second thing is the interpolant can be linear or non-linear. So what I just described last is the fact that the function, I'm assuming the behavior of the function to be linear between the 2 points. If I do a thing, let's say I take 4 data points instead of 3 data points here. Let's say I'm having a similar problem. So let's say these are the data points that are given. The data is given in the table, and I'm asked to find out the value of the function at this point, right? At this point, what's the value of the function? So this is the query point. So I can take, right, these 3 data points, and then I can fit a quadratic through it. Okay. So why should I choose just 2 data points and fit a line through that and use linear interpolation? I can always do, take 3 data points and fit a quadratic, all right, and then use that quadratic function, the estimated quadratic function, and in that function I can put as x is equal to 0.32, and I can get the interpolated value. Now somebody can say, why should I stop even there? I can take 4 nearby data points, right? For example, 2 to the right and 2 to the left, and I can fit a cubic, right? So if you have 2 data points, you can fit a line. If you have 3 data points, you can fit a quadratic to it. If you have 4 data points, you can fit a cubic function to it. So I can take these 4 data points that are in the vicinity of the query point, take these values, and then I can fit a function like this, right? So this is the cubic function that I construct using 4 data points. So I can use the purple curve, the equation of the purple curve, to find out the value of f of x at the query point. In a nutshell, there are global interpolants that are constructible. There are also local interpolants that are constructible, and the local interpolant can be polynomial of any order. It can be polynomial of order 1, which means we are doing linear approximation. You can also do quadratic, cubic, etc., etc. So this is the general broad idea. Now, people have gotten smarter and they use what are called spline functions. So when we come to this part of the course, we will discuss these spline functions, or they use something called piecewise cubic interpolating polynomial, or what is called p-chip, right? So piecewise cubic Hermite interpolation polynomial. So Hermite is, there are functions, right? You will come across when you do courses on mathematics, things like Legendre polynomials, Hermite polynomials, Chebyshev polynomial, etc., etc. So Hermite polynomial is one such family, right? And you can create what are called p-chip functions with it. So piecewise cubic, and polynomials are of the Hermite type, and they are interpolating polynomials, right? So you can use ideas from spline or p-chip, and then you can do the interpolation with those special functions. So we will get to the details of some of these things later on when we discuss the topic in detail. But just now, I want to illustrate the idea on this simple problem, right? So we have the data in the table there. And what I'm trying to do here is I'm trying to show you this MATLAB function called interperp1, right? So it is for one-dimensional interpolation. So interp is interpolation. This one stands for the fact that we are just considering one variable, x, right? You can have multi-dimensional interpolation as well, but here we are just focusing on one-dimensional interpolation. So these two lines, what I do is in the M file, I just declare the data. So whatever data is given in the table, I'm just using it. Of course, I'm not using the value of x equals 0.32 or the corresponding f of x or y value. Once I have input the values of x and y, then I'm ready to call the interpolating function. So you might notice this 3 dots here, right? So if let's say you come to the end of the line, right? You cannot type all the stuff in one line in MATLAB. Sometimes the data is long, so you have to go to the next line. So when you are doing that, it is okay to put 3 dots at the end and then continue in the next line like this. Okay, so that is the significance of these 3 dots. So you don't have to type in everything in a single long line, right? It is good to see the data in front of you, so I can use 3 dots there and I can type the other data points in the next line. Now you can see I'm calling the function, so this is yq1, That means I'm trying to find out the value of the function at x is equal to 0.32 using different interpolating options or functions that are available to me. So the function in each case is interp1. That doesn't change. So what you have to give it is the first argument is the x values from the data that's available to us, the corresponding y values, comma, then the query point. What is the query point? 0.32 in our case. We are asking what is the value of y or f of x at x is equal to 0.32. Then I'm asking it to do linear interpolation. So you can do this by hand. Linear interpolation is easy. Take the neighboring two data points, one to the right and one to the left, construct a line using those data points, and then you can get the value. So this one, right, is very useful when you're doing steam tables, etc. in thermodynamics. So if the properties, if the temperature or pressure of the steam is not tabulated, right, what we do is we take the two neighboring values, one on each side, and then we will use the enthalpy or internal energy we read off for those two values and just do linear interpolation to get the answer. So we have done this many times in high school, sometimes in engineering courses, sometimes, etc. So this is something you can easily do by hand. So when you do linear interpolation, the answer you get is 1.855. When you're using a modified p-chip function, you're going to get 1.7969. So basically the same syntax, inter p1, x values, y values, the query value, and then you have the option to specify your choice for the interpolating function. Okay, right now we are not looking at what these things mean, exactly what does it do, etc. The purpose of this video segment is not that. It is just to introduce to you the kind of problem as well as the corresponding MATLAB function that can help us get an answer to the problem. We have to look into the details. But if you use this Makima option, you're going to get a value of 1.7969. If you use splines, splines are some wonderful types of curves that was discovered about 50 years or so ago by somebody working in General Motors. All right, so the nice thing is it is extremely smooth kind of functions, but can be quite oscillatory. That's the downside of it. So everything has a good side and a downside. Okay, so if you use the spline function as the option, you are getting this interpolated value of 1.7482 at x is equal to 0.32. If you're using the p-chip function, right? P-chip function has some very interesting properties that it preserves the local shape of the function. So it won't swing as much, but it can have some rough corners. All right, that means it is not smooth. So that's the difference between the two. All of these are part of a family. Depending on the kind of behavior we think the system has or what we can tolerate, we choose one of these, Makima or Spline or p-chip. So with p-chip option, we are going to get a value of 1.7726. Note, different options give us different estimates of the value of the function at x is equal to 0.32. So which method is right? In reality, we would never know. All right, so we just choose something and then be happy with the results it turns out. Actually, mathematicians, for example, would have taken different functions, different data sets, and they would have evaluated the performance of each of these options on large number of problems, and they would say overall, this particular method, for example, using p-chip is the most accurate one overall, right? Not on every problem, but overall. Okay, so since the kind of functions we use to approximate the data, and we also have the option of choosing different numbers of data points, right? I talked about global, local, and using 2 data points, using 3 data points, using 4 data points, etc. Right? So you have different ways of constructing the interpolating function, and therefore you get different results. Okay, so if you look at the correct value, the correct value is 1.7433, right? So if you look under that blue line, right, it is 1.7433. It looks like Spline is doing a good job here, right? But as I said, it is not the best for every problem. Okay, so what we learned here is a little bit about interpolating functions. We also learned to use MATLAB's INTERP1. Thank you for your time.